Okay, so something's with iPad. Let me restart this. Okay, so as I'm restarting the iPad, hopefully that helps so you can actually see this stuff for the lecture. We can just look at the schedule. So today is the last lecture of the class on communities and graph analysis. So it's been a fun semester. First let me make a remark. Hopefully all of you who are the people who usually come to class will actually fill out the forms evaluating the course. Otherwise it's random people who never came to class and are like, typing weird stuff in there. So as the people who are here or are watching on the video, that's also great. Of you who actually kind of pay attention, it'd be great if you can rate me on the form that comes out. Okay, so I think last semester, less than like a third of the students in the class actually filled out the form. Okay. So then, what's coming up? Poster outline. It's due. It's now due on Friday at 5 p.m. By an outline for the poster. Does not need to, it's not the final. It doesn't need to be the final poster. It could be the final poster. That's fine. But I want to kind of get a general sense. Some fraction of you. How many people have made posters before? So, and what fraction have never made a poster before? Okay. So about half of you have never made a poster before. Some of you who've made it before, and some of you who have not, will not make very good posters your first iteration. Okay, that's fine. Okay, that's expected. So the hope is that we'll give you feedback so that your first poster won't be horrible. Okay, I'm actually shooting for a higher bar than that, but I want a minimum standard, right? So so we'll try and give you some other feedback as well about some design stuff. Been doing this. Been doing this number of years. Like Sanipa will give the main feedback, but I'll try and go and do that. So please also come up to me and show me your poster. Like you can bring a printout to stop by my office hours, or show it to me on a laptop or an iPad or something, and I'll give you some quick feedback. And I think that'll also help. You can do that at any point. Then the final posters will need to be printed. I think like at the end of next week. Next week, Friday, you'll send them to Chris Coleman. I posted on Canvas, the instructions are now in the PDF here. You can send that once you've been approved. So once we get feedback, you may need to resubmit to kind of make sure it hits a low bar. That's okay. Some fraction, maybe half of you will get that. It's not to be shamed. But once you get approval, you can send it to him when you're ready. Only send it once, and kind of needs to be a PDF. Okay, and then they'll be printed, ready for the poster day. So this starts at 3:30 p.m. This is the exam time. My goal is to finish by 5:30. If you really will need to leave by 5:30, kind of let me know. Last year when I did it, I was here for more than 2 hours. It took me more than 2 hours to get through all the posters. Okay, so if you really need to get out, make sure to let one of the TAs know, and I'll make sure I get through there. Hopefully I'll finish in 2 hours. Okay, and I'll, on the poster day, it should be a fun day. Okay, so you'll get to go and view everyone else's poster. You'll get to go and talk to talk to other students, see what they've been working on, you'll have to write summaries of 2 posters, which you'll just write on the back of a piece of paper you get when you show up. All right, that's still not working. If But you also get to vote on the poster. Works, great. You also get to vote on the poster that you like the best. So the person or the group that gets the most votes will get extra points, right? So motivation to make some really cool posters. Ones that have won in the past have, maybe they brought in props, or they had or even just the topic was really cool. Okay, the vote can be on anything you want. How cool was the project? How cool was the poster? It's the whole package, right? It could be more than a poster. You can bring in other cool stuff. That's all cool. Okay, and so there'll be instructions you'll be handed on the day that you get there. Any big questions on the posters? Yeah.
Is there a limitation if we make any changes or improvements from our final report to the poster?
You can put whatever you want on the poster that reflects the project, so you can keep adding stuff. The report, which probably haven't got a chance to start reading them yet, probably early next week, that'll be graded on what's in the report. But you can do whatever you want on the poster. That'd be great. Yeah. And prepare. I'll come around and I'll have like roughly, there are like 40 some groups, so I'll have like 2 to 3 minutes per poster. So that'll be what I aim for. So prepare to give me like a 1 to 2 minute overview of your poster, which I'll ask you when you come around, and then I'll try and ask 1 or 2 questions, and then I'll have to move on. Okay? So they should be ready around 3 o'clock on this day, and near the SOC, near the main office. Okay. The other thing, next week, Monday, the last official day of class is the end term test. Okay, so that'll be in class. It'll be roughly the same as it's the midterm, right? And that it will, you'll probably have roughly like 3 questions, 1 per page, and they have subparts to them. I think you should, it shouldn't necessarily take you the whole time to finish, but you're welcome to spend the whole hour. It's not meant to be something that's time constraining. You'll again get to bring in 1 page of notes, front and back, that you can use. You can put anything you want on them, but you will not be able to have any sort of electronic devices. Okay? And it will kind of mainly be on the topics since the last midterm. So think on regression, noise, and graph analysis, and kind of are the things I'd like to focus on. There might be like a sub-question that relates to something we talked about earlier. That's possible. And probably the focus will be roughly proportional to the number of lectures on the topics. Right? And so these are things that you won't have to like write code, long code. It's on an exam. You won't have to do any really complex calculations. So you should be able to write the answers and the work that you need right on the page if you answered correctly. Okay. Any questions about the intern? All right. Okay, so grades for the regression homework should be posted now or soonish. I think those will be out soon. And then the graphs homework, the last one, will be due on Monday, a week from Monday. I think that's the right date. But it's sometime in the future. It shouldn't take you too long, Okay. All right, so today we're talking about so things like structures of communities in graphs, and also and we'll also talk about some influencers, and these are in general in graphs, right? So kind of in general, we'll be thinking about graphs as like some, usually we'll, typically the input to this will be a graph which will have some vertices and edges, but we'll be often thinking about this as a social network. So now V are going to be like people, or could be other sort of entities. It could be businesses or other sort of things. And the edges are going to be like some connections on this graph, right? So if this is Facebook and you're friends with someone, then you would have an edge with that person. All right, so some of the stuff we'll talk about will have to do with graphs which are directed, right? So if I have V1, V2, and V3, I could have if I have an edge, maybe between V1 and V2 are friends, but maybe it's like on Twitter, and V1 follows V2, but V2 does not follow V1. Right? This is common if you have someone very popular, like I think like like those kids from One Direction, I guess, are very popular nowadays. Right? Yeah? No? Okay, so but I think they have lots of followers on Twitter, and so a lot of people follow them. They probably don't follow everyone back. Okay, so what's the right way to deal with these directed edges when you have an algorithm that assumes that it should be undirected, right? There's been a lot of attempts at this. Most commonly, in most cases, if you just take all directed edges and make them undirected, things work roughly like you would want. Okay? So if that ever comes up, don't, the distinction turns out not to be that major. Other ones, like if we develop, if we're talking about Markov chain on a graph, like we talked about earlier on, and it matters V1 can go to V2, but maybe V2 cannot go directly back to V1, then keep the directed nature of that, right? But if we're thinking of doing something like spectral clustering, which we talked about earlier in the semester, you can make the edges undirected, and the results will often be roughly similar than if you try to kind of model it similarly and do something more complex that took into account the undirected nature of the edges. Okay, so we'll talk in general about these graphs. The other thing about so one interesting thing we've talked about with like some of these data collection kind of ethics discussions is there exists these large graphs that are kind of in the wild, where the vertex set, might be as big as 1 billion, and this would be things like Facebook. I think Twitter is not quite that big, but there are other social networks which are in the range of have like 1 billion nodes, and so some of the algorithms. I'll mention there are challenges in scaling them up. You probably, unless you work at Facebook, you don't get to see this whole graph. Okay? So it's hard to get the entire graph for Facebook. There are some downloads, like if you go to like this Snap group at Stanford, they have this page of these large graphs they've downloaded. Most of those are more historical now. Companies, because of these privacy concerns, are wary about you downloading and making easily available these large graphs online. As it's been in the news, some of this can be found through other methods. If you're clever and maybe like slightly unscrupulous, you can often do some things to figure out how to download large amounts of these graphs, right? There are ways for the APIs that you can see, if you have a set of people participating, seeing all of their friends, right? This is what, there's some academic researcher associated who partnered with so with Cambridge Analytica, and kind of was able to uncover large amounts of the Facebook graph. But this still was not the whole graph, right? So you're only seeing parts of it, and this may have some weird effects on the analysis. So just kind of keep this in mind, that these are, you know, generally for public, these are not fully so available, right? So also on Twitter, you can download a part of the tweet stream, and you can kind of figure out somewhat who is following who based on some public information, but it's hard to reconstruct this entire graph again. Okay, so there's some limitation, but assume you're working for a company or you've collected some smaller graph. How can we analyze it? Okay, so this is very different from, say, 20 years ago, maybe even 10, even like 15 years ago. Let's say, you know, 15 years ago, there was a lot of research on these large graphs, on thinking about graphs from both a social network analysis and from a mathematical standpoint. But they were kind of broken in a couple of ways. Okay, so in the math world, there are a lot of these large graph phenomena that were studied under what's called the under what was called the Erdos-Renyi model, and this was, and you would say a graph with NP. This means it has n nodes, and each edge between a pair of nodes exists with probability p. Right? So if each edge exists with 10% probability, then I would independently generate whether an edge exists for each of the pairs of these vertices. Okay? There's similar models where instead of p, you would say, make this independent. I want to say there were exactly so many edges in the graph, and the subset of those edges was chosen at random. Right, where this says in expectation I'm going to get n choose 2 times p edges, but sometimes it's more, sometimes less, based on this. So this describes a random process for generating graphs, and then you can study things like for what values of p does the graph start to become fully connected, where every edge is connected to every other edge. Right, and what happens is you start to have these small connected components. Then you get, at some as you increase p, you get this really big connecting component, and you get these small things off to the side, and then eventually everything is connected. The last thing to be connected are usually these isolated vertices, and there are these phase transitions between stuff that happens. There's lots of beautiful math in this world. Okay, so real-world graphs don't look like this. So these are. Let's say these are not real, world models. Okay, real world models don't look like this. They're kind of, the edges tend to cluster in some way. They tend to be these connected communities in these graphs that you did not see so much in this model. Right, and so people studied this model and lots of cool stuff, and we knew lots of things about it. We knew how to generate random graphs this way, but it was a poor replacement for these graphs that we couldn't see that we wanted to study. People, at some point I was an intern at like Yahoo Labs. And they had all these different social networks inside of Yahoo, and while I was in the company, I was able to kind of look at these graphs, right? And it was commonly known that they did not follow this model, and so people are coming up with other models, which we'll discuss, which are replacements for this model, which did a better job thinking what things are like, so we could generate graphs to replace the ones that we don't actually have access to. Okay? The other side of this story is that in the sociology, I think I spelled that right. So this was like the math world. In sociology, people wanted to study the interaction between people in groups, right? So they would go and they would try and create graphs of people, and so there would be like these famous, there's this really old graph from this karate club, and it has like roughly like 30 nodes in it, 30 vertices in it. There's also things where you would go to a high school and you would look at the friends in the high school, and you would go to the high school, and some sociologist would painstakingly interview all these people in the high school and try to understand how these edges were connected. And so this was a lot of work, and you could have that the size of V was maybe 200. Okay. So these are pretty small scale graphs. You know, there was, and they were really pain to collect. And a few things were fairly common about them. Is you could usually draw these graphs, right? You could write down the edges, you know, the vertices in some way, and you could draw the edges between them, and you could kind of see what was going on. Right? When you have 1 billion nodes, for one reason that's not possible, is just there's so many nodes. The other reason is that there's so many edges, to draw them, that they're not planar. You cannot draw them away without having lots and lots and lots of edges crossing over each other. These may not have been exactly planar, but they're close enough that there weren't too many intersections, and if we draw them, we could figure out how to kind of visually see what's going on. Okay? These are also small, and so some of the features that, kind of interesting features that happen in graphs did not really occur at that scale. You need to see thousands or more of these vertices before you start to see certain types of clusters in the graphs. And so people didn't know, did these types of clusters exist? You know, or what type of clusters were naturally there? Was it good to look at just to find, like, there's idea of a clique in a graph. Right, I heard this from like an algorithms class. Right, this is a set of vertices where there's an edge between every pair of these vertices. Right, and on small graphs, this is a good way to kind of find communities. In larger communities, you don't have all of the edges. You may have most of the edges. Right, but in small scale, this kind of, if you have a group of friends, they all kind of hang out together. Right, but if you have groups on Facebook, some people don't talk to each other, but you still have a clique. Right. All right, so kind of as an example of one of the questions that I like to highlight, that we could start to study around 15, 20 years ago, was why do people join groups? Okay, and there were a couple of kind of theories about this from sociology, and they really didn't have the data to back this up, so they had theories instead. And so we're going to look at these. You're going to have some group that's evolving over time. So these are people who are involved in a club. They're like in church together, or this is a church everyone's involved in, or it's a class people are thinking of signing up for. Okay, and so there are two people who are thinking of joining the class. So Xavier and Yolanda, right? Like, okay. And so they both have 3 friends in the group. All right. So I'm going to try and look at 2 different models of why people join group, and kind of try and remove out all the other variables. So with Xavier, has 3 friends. Okay, and all of these friends inside of the group are connected to each other. They all have internal edges. Okay? And Yolanda also has 3 friends in the group. Okay? But these friends are not connected to each other. And it could be that the average degree of the friends inside the group is the same. Everything is the same except Yolanda's friends are kind of disparate parts of the group, where Xavier's friends are all part of kind of a sub-clique within the group. Okay? Okay, so who is more likely to join the group?
Xavier.
So you think Xavier is more likely to join the group, and so why is that?
Because if he were to join, he would automatically be part of that clique. Because he has edges to all the other ones, and they have edges to each other. Whereas Yolanda, if she were to join, she would just, I don't know. It's just like a...
Yeah. So the argument for Xavier is kind of gets to join kind of a close group, and who wants our? Yep.
Well, I think in addition to that, since they're in this clique, they're going to be more persuasive towards him. They can join forces in trying to get him to join the group, whereas for Yolanda, those friends might not come together and convince her as well.
Okay. Does anyone want to take this? Does anyone want to take this, like the position of Yolanda?
Maybe Yolanda could have a different perspective of what it is to be in that group. So
Yeah.
maybe.
Adding information.
Perspective. Yep.
Catch up, maybe.
What?
Catch up with these disparate people.
Oh, so she could see them independently.
Yeah.
Right, yeah. So there is a theory called independent so independent support, in that you would have, if you saw these, if Xavier saw these people, he would see them all at once maybe, and they would say, oh, you should come join our group. Where what would happen with Yolanda is one person at work, one person in the neighborhood, and one person kind of in another group. She knows all of them from different ways, and they all said you should join this group. So she's getting independent support from different factors. Or maybe she's getting a broader perspective of what's going on in the group. Right? And so, prior to being able to observe large graphs dynamically on the web, there were these 2 independent theories of why people join group. Either they had they get to join a close-knit group and they had kind of a persuasive clique, or there was this independent support and they had this broad perspective of what was going on. Okay, so let's vote. And no one knew the answers. There were camps on both sides before we could collect data. So who thinks that Xavier is more likely to join the group? And who thinks Yolanda is more likely to join the group? Okay, 50-50, very good. I did a good job of painting the perspective. Okay, the answer is Xavier is more likely to join the group. Okay, well, we learned this by observing this behavior over time and kind of looking at these types of people, breaking them into situations where they're basically identical, except kind of the Xavier's friends are grouped together and Yolanda's are disparate, and Xavier was more likely to join the group. This idea of being part of a clique seemed to have something to it. Okay, so these are the sort of things that we could questions we could start to ask that we did not know how to ask before. We just couldn't collect the data. Okay? So this kind of is related to a model called preferential attachment. Okay? And so it's not exactly the same as why do people join groups, but it's kind of a very closely related idea. And that's that let's say, basically I'll summarize it as new edges are more likely to form triangles than so then random, right? So if I put down a random edge, the probability it forms a triangle. Like if I do this in like the Erdos-Renyi model, where every round I pick a random pair of vertices which is not connected, and I add an edge. That's on average fairly rare. It's going to form a triangle where the two edges is connected, have or the two things that's connected. Those are both connected to each other, or they both have a common friend, right? So if I have I and J, let's write this a little bit. So if I have I and J, and I'm thinking of adding new edge here, then there might be a common friend, right? So this edge is more likely than a random edge that does not have a common friend. So this could be in social networks. You have Xavier or like Bob and Sue both have a common friend Kate, and they said, oh, you two should talk, right? So something as simple as that. That's how you can form an edge, right? This seems very like a logical thing to happen. And so indeed this is observed in the formation of networks. Okay? And so this is not not the same model as the Erdos-Renyi. Okay, this tends to have graphs that, like, if you looked at, I looked at the adjacency matrix, I took I looked at the eigenvalues of it. These tend to decay more sharply than if I did it at random. I'm going to tend to have more concentrated groups. Okay. Yeah, and it could also be that they're joining because they're part of a common group, so it's related to the other thing. There have also been kind of some empirical studies that have come out of this, where if you have kind of something related, if there are if kind of node I has a few triangles, or fewer triangles than average, then this person is more kind of likely likely depressed. This is typically someone who is not as socially engaged with the community. They're meeting with one-off people, and there's some studies that I had seen empirically that said kind of these sorts of people in social networks had a higher rate of depression. You could start to make these sorts of conclusions, and it's kind of related to this preferential attachment. You might be also to say, so if too few or too many of these triangles, then is this the bot? Right? So this is another kind of common thing people have looked at, is that there are these now could be I've heard reports that between 10% and 50% of the accounts on Twitter are actually bots of some sort, depending on what you mean by a bot, right? So sometimes, and that could be as thing as every account on Twitter is supposed to be, if there's supposed to be a person, then things for companies might classify as this. But the lowest number I've heard is 10%, right? A large fraction of them are not actually associated with an entity that's using it in kind of the originally intended way. Now, some of these bots are like, there's this, it's like it's like horse ebooks or something like this. Has anyone heard of this Twitter account? It was up a while ago. It seemed to be generating random phrases that were sometimes kind of hilarious. And it seemed like a computer program. It turned out it was actually a person who has just been generating thousands of these for years. He would just think of random phrases and kind of type them down, and then had it so it would upload them every so often at some random sequence, or maybe it was a couple people. And people thought it was a bot that was somehow putting together language in strange ways, and it had accumulated like a following. That turned out not to be a bot, but there are lots of other bots out there, okay, that are not like trying to influence elections or something like that, right? But sometimes these bots you can find because they're created. The other thing this comes up is people try and buy followers on Twitter, right? So I think was it like one of those Chicago, one of the movie critics from Chicago, I think bought some followers on Twitter, and you can kind of detect the followers by looking at who's following these people and seeing who else they're connected to, right? And they tend to be, they have connections to other people, but they tend to be connected to each other in some way more than random people. And you can kind of find these connections, and kind of, there have been algorithms that try to figure out who bought followers by looking for patterns in how these are done. And it's often by looking, the simplest statistic you can do is for every node, look at the fraction of triangles it's in proportional to its degree and compare that to the entire set of graph. And that's a pretty good kind of indicator of, is this a normal sort of interaction with the network. Okay. So these ideas of triangles is a fairly kind of important one to understanding the structure of these graphs. Okay, so this is just kind of a conceptual way of thinking about it. Let me talk about two more kind of actual analytical properties that you can calculate in graphs. I'll do two or three, and I think that'll be what we finish the lecture on. So the first one I want to talk about is a notion called betweenness. Okay, and like they've run out of non-strange names to come up with things, so they call it betweenness. And so the idea is that you have some graph. We'll say A and B, and this will be an interesting edge right. So you have some graph that maybe looks like this, and so then the betweenness of A and B is going to be the fraction of the shortest paths that use edge A, B. Okay? So how do I think of the fraction of the shortest paths that use edge A, B? I look at all pairs of the vertices V1, V2 in the vertex set. Usually I assume the graph is connected. Otherwise, if there's no, then the shortest, if I can't get from V1 to V2, then there's no shortest path. It definitely does not go through edge AB. Right, but let's say that I have V1 here and V2 here. Okay, so now the shortest path to get from V1 to V2 probably goes like this. And then it's a little tricky here. So I go 1/2 this way and 1/2 this way. Okay, so this is the shortest path between V1 and V2. This is 1/2. Okay, and I look at all pairs and I look at the fraction of the shortest paths that need to use this edge. And sometimes the shortest paths are split, so I say, well, even if I pick V1 and V2 half the time, it would use kind of, if I want to look at this edge here, then half the time it uses that edge. So it counts as using its, instead of counting as, I get half credit for it. And sometimes there's third credit and eighth credit and so forth. Yeah.
What about the line following it? Is that still 1 or is that also half?
Well, that one is not on the shortest path. So these sorts of edges out here, so these, you see that? These are going to have low betweenness score. There's going to be very few shortest paths that are going to use these edges. It would only be if it included a vertex that was in this dangling part out here. Right? Where the ones that are in the color in the middle here, these are going to have high betweenness score. These in here, because anything that's on the left side, one vertex, and on the right side, the other vertex, which is roughly a quarter of all the paths, are going to have one on the left and one on the right. They're going to need to use these two edges. Right? So these are going to have a high betweenness score. Yeah.
I was just wondering, is it NP hard to find the betweenness of an edge?
No, you can do it in polynomial time. So the algorithm is a bit kind of technically, it's a bit messy to describe, but you start by you find all pairs shortest paths, right? Which is something you study in algorithms class, right? You can do all pairs shortest paths, and then you can just for each of the edges you can calculate this. So you can find all these paths and then just annotate each edge how many exist. You have to be careful with the splits, what you do here. So actually, the right way to do it is for each vertex. So iterate over all the vertices for one edge of the paths, right? And then find all the shortest paths to everything else. And so it's kind of like do it with something like Dijkstra, where you're doing a breadth first search coming out. And sometimes you split, so it's equally short to go to V2 through these two different channels. So once you get out to the edge of the Dijkstra tree, then you come back, and when I come here, I split the contribution of going to V2 along these two paths. Right? And I annotate this on the edges as I'm walking back. Right? So I start at the bottom of the tree and I walk up and I'm accumulating if V2 was at that location or it was at this location, then when I go back on this dark green edge now, I'm going to have I'm going to contribute 1.5 to it. Half from V2 and 1 from starting at that light green vertex. And then when I get back to the edge AB, I'm going to get both of the 1/2s, both of those 1s, and then also if I start here, so I'm going to be adding 4 onto edge AB, right? And then 5 onto the edge next to AB and so forth. And I can kind of count this as I walk back up the tree, right? And so this is kind of roughly how you calculate this. Yeah.
So besides the shortest paths with the minimal spanning tree also accomplish this goal?
So you can do something like instead of doing the shortest path, you can. So there are lots of. I think there are lots of ties in the minimum spanning tree here if edges don't have weights. So you might have lots of minimum spanning trees. So you could do like a distribution or minimum spanning trees. There are other versions of things like betweenness that give a similar score. This is kind of one of the more dominant ones. Okay, so you could, but in order to calculate specifically this, I don't think you can do it with the minimum span tree. I think you need to handle, it's kind of a little bit tricky because you have to take care of these splits when there are multiple shortest paths kind of in a careful way. And I'm not sure how to do it that way.
Is it required to have an edge between A and B to define betweenness? I mean, is it possible that I have like A connected to B and B connected to C, and I want to calculate the betweenness between A and C?
Oh, between A and C. And so whether that whole segment is on the shortest path instead. Right? So what you're suggesting is, like right now, so let's say I've got, this is edge C up here.
Can we get right one as C? So B to C?
Oh, B is B to C.
Yeah.
C up here.
I want to calculate the betweenness between A and C.
Between A and C.
Yeah.
Right, so I would care about if those, like A and C itself has no edge between it.
Yeah.
So the betweenness is 0. Right, but I could say, let's say I wanted to look at the betweenness of the sequence A to B to C.
Okay.
Right? How many times does that sequence fall on the shortest path? Right, so this is definitely doable. This is kind of like an extension, like where we looked at the bag of words model for words, and this would be like the 2 gram, the bigram version of this, where I'm giving a score over all sequences of 3 parts of the graph. Right, and this is not an unreasonable thing to do.
But what qualitatively does this betweenness define? Because
Okay.
there is some similarity between A and C, but if we say by definition betweenness A and C, you said that that's going to be 0. But
Yeah, right. So what I'm specifically giving a score to is an edge. So this is supposed to capture how important is the edge A, B. Right? I'm trying to give it a score to the importance of this edge. So like if I were to remove this edge, like how many shortest paths, what fraction of the shortest paths would I change? In this case, I would actually make the graph so it was not connected. Right? But a lot of graphs there's multiple, assume there are multiple connections. I would change if a quarter of the shortest paths went through this edge, which would be a pretty high score, right? I would be changing a quarter of the shortest paths. And that would be a significant change in the graph. Whereas if I change one of these edges in the light blue out on the tails here, I'm changing like 1/15 of the shortest paths. That's not a big deal. I don't affect a lot of these things, right? So think of it as, like instead of a social network, think of it like the cables on the internet or on like the connections on the internet between routers, right? If you're routing packets, you generally kind of go something like the shortest paths. There's some kind of resilience nature in how it does routing, but if I remove a link goes down, and that was on a quarter of the shortest paths in the internet, I'm going to slow down a lot of the internet. Right? Can you think of important connections on the internet?
Just like the wire that goes across the Pacific? Or
Yeah, right. There are these wires, if you don't know this, there are actually lots of wires that go between Europe and the US and the Pacific and the US, and these are underwire and they carry a lot of information. They're in a lot of shortest paths, and if those get cut, the internet going across these things could slow down a lot. Right? There's more than one wire, but they're actually these really thick wires that send information. There's been reports of some unfriendly nations that have put submarines near some of these wires, and we're like, what's going on? It's because these have high betweenness score. Okay, these are important wires, and they carry the internet. You know, if you think of the internet as like all in the ether and the air nowadays, because you're in the Wi-Fi generation, most of the data is actually moved. I think still through cables, although that's changing. Okay, so this would be really important edges, right? Okay, so this, between this and like PageRank are kind of, they're probably the two most common ways of describing the importance of objects in graphs. And they're measuring something kind of different in certain senses. They aren't exactly the same. They're capturing different properties. And there are other variants of these as well, like you could look at the distribution of minimum spanning trees, what fraction of these use a certain edge. You know, that's a perfectly reasonable thing to think about. It's just not as common for whatever reason. This one is not as efficient to compute, and is not generally very scalable on large graphs. It's also not terribly resilient to things like compressing the graph first. That often has pretty big changes to it. So attempts to kind of compress the graph, like sparsify the graph and then run this, can give kind of big enough changes to this that it's not that effective of a strategy. So this is kind of a tricky concept to compute, whereas PageRank is something, because it's related to the eigenvectors, it's something that we've studied a lot how to do this at scale. There's been some work in the last few years that has kind of looked at how to compute this at scale, but for a while this was kind of a known useful quantity that was hard to compute. Okay, I'll mention also that you can you can also define the betweenness of just a single vertex. Right, so if I just want to find the betweenness of a single vertex, so how would I do that? Yep.
See how many shortest paths have to go through that vertex.
Yeah. All right, it's basically the same thing. What fraction of the shortest paths go through the vertex? I can do the same sort of calculation as before. Instead of accumulating the weights on the edges, I accumulate them on the vertices as I kind of do this Dijkstra and then retract it back through. Okay, so you can define this on the vertex. So again, now this is more directly comparable to PageRank, which is also giving an importance score to these vertices, and these are capturing different sorts of properties. Okay. Okay, so this was about finding communities in graphs. So then how would I use betweenness to find communities? What would it mean to be a community on a graph? And what would, and how would I use betweenness to do something like find this?
You could split at the locations, at the edges that have high values of the zeros.
Yeah, so remove the high betweenness edges, then then the remaining connected components would be like would be the communities on the graph, right? So if we did it in this example here, what colors do I have left that you can see? Okay, let's try this. These edges would AB and AD would have high betweenness. If I remove them, the remaining parts of the graph would be here, and these would be the communities in the graph. Right? There aren't the betweenness scores inside of any of these edges would not be as high because I wouldn't necessarily need to go on it to go back and forth between these different parts. So these might be the communities of the graphs if I took out the high betweenness scores. Right? So this is a way of finding the tightly connected components, and then the betweenness kind of edges are the ones that are like the important linking edges. They go between different communities on the graph. Yeah.
What's the difference between the betweenness and the cut of a graph?
Yeah, so I mean, the other thing you could do is you can try and do a cut. A cut has a property, so you could say what edges have the highest normalized cut. So a cut is defined by you completely partitioning the vertices into two parts. If I remove just one edge, I don't necessarily do that, right? I might have another edge that goes here between D and C. So if I cut the AB edge, then it's still connected, right? So the cut talks about cutting a number of edges all at once, where the betweenness are just scoring individual edges. Yeah, so the cut does not really give you a measure that lies on top of the edges or the vertices, where the betweenness does, and you can kind of use the betweenness to find cuts by keep removing them until, in sorted order based on highest score to lowest, until it becomes disconnected, and maybe this is a way of finding cut. It's a perfectly reasonable way of trying to divide up the graph. Okay, and it would probably do a good job of balancing the clusters, just like the normalized cut, because in order for you to remove a subset of edges and do this, you would need to have shortest pairs that go from one half to the other typically, right? So you need to have roughly the same number on either side. You're kind of multiplying the two fractions together to get the number that cross over the middle. Yeah. So that would probably work reasonably well and probably give you something somewhat similar to normalized cut is my guess.
Could the degree of a vertex explain its betweenness?
So the degree is a tricky quantity. It might, like a high, so a high degree graph node could be one of these could be useful in one of these like small world phenomena where you there are these ideas on graphs where you can get to from any one node to any other node with a small number of hops. And this often works because there are certain high degree nodes where if it feels like the Twitter graph, so many people are following these people in one direction that if you know someone who follows someone in one direction, then probably someone else in a different part of the world also follows them, and you're all of a sudden connected. So it goes through these high degree nodes. Now, it's the edges that are important, and so you'd often be edges that are between two high degree nodes, but might have high betweenness score. That could be possible. That's a good conjecture, I think. Yeah.
Is that supposed to be a pun that the connection is going in one direction?
Oh. Yes, that was intended. That was intended all along. I'm just gonna roll with it. That was a little bit of a lie, but okay.
What happens with A once you cut those? Does A kind of disappear?
Yeah, A would be in neither community under this model. So yeah, so communities are often, and I distinguished it from clusters, are not partitions. Okay, so clusters we talked about as partitioning the nodes, and every node was assigned to some cluster, right? Or maybe it was soft clustering, and so half it was one cluster, half was another. Communities does not need to be that. It is a tightly connected subset of the graph. Okay, they can overlap with each other, and they, if I have a set, a set does not need to partition V. Okay, it does not need to partition the vertex set. I'm just trying to find regions of the graph that somehow indicate that there's some sort of there's more connections than I would expect at random, essentially. Okay, and there are multiple ways to define this. And so this brings me to the next kind of thing I wanted to talk about, is there's a very common measure to define the score of a community called modularity. I don't know where that comes from. It comes from people in physics, actually, who started studying graphs. So it might be related to some terms in physics, as far as I know. Okay, but this is defined on a subset, C subset of the vertices. Okay, and so you'd often, it's often called Q of C, is going to be the fraction of the edges in C in the group minus the expected number, or the expected fraction of edges in the group. Okay, so that would mean I'd have a part of the graph where I'd have a lot more edges than I would expect. Okay, and one of the smart things about it is that it did not define the expected number of edges based on just the Erdos-Renyi model. Okay, it didn't just say if there are k edges in there, then I expect k choose 2 times p edges if the rate of edges is p. Right? It did not just make a simple model, it took the degree of the vertices into account. Okay? So let's define this a bit more precisely. To define this, I need 2 parts to it. I first need the adjacency matrix of the graph, and this is Aij equals 1 if edge and 0 otherwise. Right, so this is typically the adjacency matrix we've seen before. And so this is, basically what I would do for the number of edges in is I'm going to, the fraction of edges will be something like 1 over something to normalize here, which I'll describe in a bit. And then for every vertex, let's say j in the subset, sum over all the vertex I in the subset C times Aij. Right? So I'm summing how many edges I actually saw. I get a 1 if I see the edge and a 0 if I don't. So I'm looking at the subset of this adjacency matrix defined by the elements of C. And then for the expected one, I need to do, again, 1 over something I normalize by, where I sum over I in C, and I sum over j in C, and this is Eij, where I have some sort of expected matrix. So I somehow need to populate how many edges do I expect to have between I and j. And it's going to be basically the difference between these, and there's some term here I haven't explained yet, which I normalize, but it's just some scaling factors, so it turns out not to be too important. Okay? So the adjacency matrix, you understand. The expected matrix is going to be a little bit more interesting. So the expected matrix, Eij, this is going to be equal to di times dj divided by 2 times the total number of edges, where di is the degree of the vertex vi, which is equal to the number of edges which include vi, right? So I look at all the degree of a vertex, right? So if this guy right here is vi, then di is going to be equal to 5. It's got 5 edges. Right, so this expected number is now dependent on the degrees of the vertex, right? So if I have a vertex I that has a really high degree, it's one of these guys from one direction. Now I'm conscious about this undirected graph line. Okay, great. Okay. So Harry Styles, right? Is that his name? Yes?
Yeah.
Okay, good. Harry, he was in that movie too, Dunkirk. Okay. So Harry Styles, maybe he's got a huge number of followers. So if I look at an edge, I expect, it's more expected to see an edge between someone and Harry Styles, right? And then maybe the other edge is going to be like so like Taylor Swift, right? Maybe Taylor Swift and Harry Styles have an edge between them. This would probably be, this is not so unexpected. They both have so many edges involved, right? So might expect them to have an edge. That would not be that, as interesting. So now, in order to have a high modularity score, I'm basically subtracting off the expected thing. So I don't end up just finding clusters that have vertices that have high degrees. It would have vertices that have high degrees. That's okay as long as there's a lot of interconnections between them as well. I'd expect a lot of connections if they all had high degrees, right? So, so let's say there's a group of your friends who. So I've done this in the past where I've asked, like how many friends you have on Facebook, right? And usually in the class there's someone with over 200 friends on Facebook. Does that seem? Yes. Yeah. We've had people over 1,000 friends on Facebook. Anyone? Yeah. No. Yes. Yeah. See? Okay. So some people have 1,000 friends, right? So in order for you to be to be useful as part of a cluster, you would have to be a lot of your friends, maybe you have a lot of friends back home who all have like 1,000 friends, but you're all connected to each other. Maybe everyone from your from your college or your high school, you all have a lot of interconnected friends, and you're just all very active on Facebook, right? So this would be a good example of a cluster. But if you have a lot of people with friends, but they're not connected to each other, then that doesn't show as tightly as a tightly connected subcommunity here. Okay. Okay, and so then a community is just then the goal is then just to find a subset of vertices with as high a modularity score as possible. All right. Yeah. Let me write out. So typically you define this as 1 over 4e, then times the quantity sum over j in C, sum over I in C, aij minus eij. Right, so then this is the modularity. And so I just want to find the community, the subset of vertices, that has as high of a score here as possible. Okay? So unlike things like k-means clustering or PCA, where I have this issue of what is the right value of k that I want to do? Or if I do spectral clustering on a graph, how many times do I want to split until I stop? This, by the looks of it, it does not have any parameters in it. I can just look at the graph and I can say, can I find the subset of vertices with as high of score as possible? Right? So this was a very attractive model because it didn't depend on the like Erdos-Renyi model. It was adjusted to the degrees of the graph. So if I have these varying degree structures, they're not all roughly the same. It accounted for that in what it meant by the expected matrix. I can define the quantity of a community without having some magical parameters in here that I have to kind of choose to tell me what scale I looked at. It kind of automatically figured out what is the right, maybe it can automatically figure out what is the right scale. Okay, so this was very attractive for modeling graphs for these couple of reasons. Okay, so now, as I mentioned before, this was developed by people from the physics community who are modeling these dynamic systems. They were not computer scientists, so they came up with this model first, I believe, and then they decided, okay, now we need to compute this. And it wasn't like developed hand in hand, like spectral clustering. Okay, we have this tool. We can compute eigenvectors. How do we turn this into a clustering algorithm? That's a computational kind of view of things. This is kind of more from the modeling perspective, as this would be a good measure of, is a subset of the graph really more connected than you would expect? But they didn't initially think too much about how do we compute this. Right? This is something that kind of, it's been a study of later on a large graph, how do you compute the subset of vertices with the highest such score. Okay, and so I'm not going to tell you any magical way how to do it. There are a few things you could try. You could start by doing spectral clustering until, and keep dividing the graph until the modularity score starts to decrease. It should be increasing as you keep splitting until it decreases, and then you can stop, and that would give you, kind of tell you when to stop doing splitting on spectral clustering, when a split will actually decrease the modularity score. Okay? You could do the same thing with some version of k-means or something like that, where the center was one of the vertices in the graph, and the distance was the number of hops you had to do. Right? You could come up with other sort of clustering measures here. You can also try some greedy approaches where you have a subset of vertices in the graph, and then you try to add a vertex into the cluster C, into the community C, and you see if it increases the modularity score. If it increases, you add it. You can also see if there's a vertex in the cluster that decreases the modularity score. If it increases the modularity by removing a vertex, then you take it out. Right? And you can, these algorithms are a little bit brittle. They can get stuck in local minimum pretty easily. Kind of a little bit more aggressive strategy is to find all of the vertices that individually increase the modularity score and add all of them. Now that may not increase the modularity score, but it will allow you to kind of explore, kind of make a bigger jump, or maybe you add all of them above a threshold, right? And it'll allow you to explore a bigger chunk of the space. It's less likely to get stuck in local minimum. So there are a variety of heuristics you can try to compute this, but this is nice in that it really doesn't depend on external parameters in order to fit this. Okay. Now, I want to mention that that might be a little bit of an untruth again. Technically there's kind of a hidden parameter in here. I can do something like, I can put a regularizer where I kind of normalize I weight the adjacency matrix versus the expected matrix in a different way. By default, this is gamma is a parameter 1, but I could set it to be something else. And there's been some work that has explored setting this to be something else, and this kind of, sometimes this is better. It helps you it can help you focus on different scales of the graph. These modularity structures in the graph tend to occur at sort of like a somewhat medium scale. They tend not to be too small parts of the graph. Okay, so maybe there is a parameter that's lurking inside of here instead. Okay, but it's pretty default to use this as a 1. Okay, maybe I'll mention one more thing very, very quickly. A clique in a graph is a subset of the vertices where all vi, vj in S have the edge vi, vj in the set of the edges. Right, so this is for a graph. Okay, so these cliques in the graph. So cliques are like it's NP hard in the size of the clique to define the largest clique in a graph, but these are kind of useful properties to find. And aside from cliques, there are other kind of substructures in graphs. Maybe I want to find a substructure that looks like a square in the graph, or maybe a set of 5 nodes where one is connected to the other 4, and then there's a set of 4 nodes. And I find these sort of substructures in graphs where the triangle is kind of the base substructure, right? Where like the triangle, as I mentioned before, is kind of the smallest thing we want to do. There's a lot of work in kind of counting the number of triangles in the graph. This has to do with like the clustering coefficient is a term that has to do with roughly how many triangles are there in a graph. But you can count other substructures. How many cliques of size 4 or of size 5 are there in a graph? Can you detect all of them? Within this problem, and all of these finding these motifs in the graph, there's kind of a common, really best algorithm how to do this. It works at a typical RAM model, and there are extensions into like these distributed MapReduce models. But the idea is kind of define all of these motifs is going to be like this a priori algorithm for counting these frequent item sets. Okay, and this is going to work where basically you find all edges in the graph, or maybe you have all the edges, and then you search kind of these things where you have 2 edges, edges 2 which are adjacent, to check if there's a triangle, right? I check if there's an edge here. So I look for triangles by looking at an edge, looking at the vertices of the edge, and looking at other edges on this vertex, and then I see if that's connected, right? So I search for triangles by starting with pairs of connected edges that I know I can find and checking to see if they're connected, right? And then I search these triangles and these overlapping triangles to see if there is a 4 clique, to check for a 4 clique, where after I found all of the triangles in step 2, then I can find, for each triangle, I look at an edge, I see for this edge which triangles is it part of, and then for each of these triangles that this edge is part of, I check if there's this 1/4 edge, and if there is, it's a 4 clique, right? I know there must be this common substructure in the 4 clique that I would have already found in the previous step, and I want to build them up incrementally, and usually the they're the most edges or triangles, this is usually the highest number. Usually the 4 cliques are smaller than here. So it starts getting faster after you do this step. And if it's roughly the size of the number of edges, if it peaks here, or the number of triangles is not too many more than the number of edges, then this is a feasible runtime to compute. So you can compute all the cliques. And in typical graphs, this makes it actually feasible to compute all these motifs in this way. Right? You could pick another motif that looks like that or like something else. And people have looked at computing these motifs and using these to understand different structures in the graphs. And so again, the algorithm you should use is building from the bottom up and kind of keep using that to bootstrap the next more complex layer in the process. Okay, so that's it for this lecture. That's it for the lecture for the semester. I'll see you next Monday for the interim exam and at the poster session. If you want to look at example posters again, I have them up front. Please fill out your teaching evaluations, all of you who actually come to class. Thank you.